Dude, I have two classes like this. Math and history.
Apparently next semester our Spanish classes.
Go on.
Say something there. Oh, there you go. Good job, Nominee. What's up? Oh, you just weren't on the TV for just a few seconds, but then as soon as you start talking, you beat out Chippewa. Maybe it starts in Chippewa, because it goes alphabetically, and you guys don't make noise, it won't switch to you. I don't know. Don't know what's going on. All right. When we left off our Fearless Adventurers, we were on page 259. And we were looking at this graph, and I had shown you the two spots where we were not able to, oops, I got to go a different way to get there. Let me see. How do I do this again? Go here. Go here. Go here. Go here. Go here. Go here.
Go there.
I know, it's just stupid. Check my email. Nope, you don't really want to check your email. Say yes, and it'll say something went wrong. Backtrack. And now I can get to my files. Isn't that just... And they said, this is going to be much better for you, Kevin, than our old plan. Well, I can understand what they mean, because the old plan was very unsafe electronically, because people could go in, and we had teachers, honest to goodness, who would click on links that said, I don't know what they even said, because I'm just like, dude, don't click on anything. But they would click on links, and then what happened was some nefarious creature decided to go into one of the faculty members' paychecks and try to route it to a different spot. And so ever since then, the school has been like, ugh, on our case like crazy. So, in view of that, we get to now take forever to find our files. But the advantage is nobody's going to steal my paycheck. So, for the bad, I will put up with the good. Okay. As I said, we're on page 259, and we're talking about why does it not go to 259? There. We're on page, no, it's not 259. Well, yeah, it is, but that's not the page that it is in here. I see. They're off a few pages. Okay, here we go. So we're on lesson 19A, and we're talking about this graph, and we got to the spot where we know what's happening on the left. Oh, we can't see that. We know what's happening here on the left-hand end of our graph. As you go farther and farther towards the negative, our function gets closer and closer to 0, right? Over here on the, well, not 0, a value really close to 0 for right now, okay? As we go farther and farther over to the right-hand end, it gets closer and closer to 0. Yeah, I said it was 0, but we don't know exactly what it is. We know it's something close to 0, because if you look at the graph here, look at our values start here at 5. It looks like it's less than 1, right? But it's not necessarily 0. We don't know exactly what it is, but we're going to find that out. But we do know stuff that happens in between time. Here's an asymptote. What happens at this first asymptote on the left-hand side? If we're up on this side of it, we're down on this side of it, right? If we're up on this side of the asymptote, we're down on this side of the asymptote. See if the person sitting next to you can figure out what's going on in this yellow region. Go.
Is he better turning around to the blank space right there?
What do you think? Tell us.
Is it just a parabola?
It's just kind of like a parabola. It's going to go up, reach a top part, and go back down. How do you know it doesn't go all the way up and down?
When you're not here, I keep it up. When you are here, I keep it over.
How do you know?
I thought it was like a vertical parabola because that's where each of the spots left off.
Yeah, right. So it's going to be a vertical, unbelievable. It's like I saw you coming and I closed the door because just as I was closing it, you got there. It had nothing to do with you. I was not. Oh, okay. Truth be told, I was trying to lock you up, but I got caught. So anyway, we know for sure it doesn't cross the river, right? Everybody agree? If it crossed the river, there would be a root here. No root. So it must go up and come back down. Could it go down and come back up? Yes, if this root appeared twice and this root appeared twice, right? Then it could come from the top and then go back up. Could we figure out what's happening in here? Sure, we could find a value that's between -1 and -2, or -2 and -1, and try it and see if it's positive or negative. If it's positive, our graph will be up here. If it's negative, our graph will be down here, right? In this section here, all you can tell is that it's really close to the river all the way along there. Maybe he stepped into the river to try to ward off anybody that was trying to track him and then jump back out, right? But at some point, cross from the top side of the river to the bottom side of the river. Right? Everybody agree with that there? Okay? This section is the easiest one to tell. Nothing's happening in there. We know for sure it goes through this point. We know for sure it's up and it's down. That's an easy section to tell. Page 259, down at the bottom. It says, suppose we could take this rational function that we know is f of x. If we did, we would know it's a composite of p of x and q of x. Well, that's interesting because once we know p of x is going to have roots. Okay? Places where it's 0. Those are very useful because they will be zeros of our function, of our f function. Q, if it has zeros, that will be very useful too because that will be vertical asymptotes of our function. Okay? So that's where we're going to start right now. Let's look at page 260 and let's look at P, the numerator function, and Q, the denominator function. So here's page 260, and this is the P function, the numerator function. Can this graph be used to determine the zeros of f? F of x zeros are at where? Where are p of x zeros? Same spot. What are they? X equals 0. Very good. 2, 3 twice. It is important that you write 3 twice. Do you remember why we had to write vertical asymptotes twice? Because it was one that made it so that the function would go up on both sides or down on both sides. What do you think is true if that root appears twice? Well, at 2, I'm going to both step into the river and step back out of the river, okay? I'm going to cross the river twice. Well, the only way you can cross the river twice at one point is to go in and then back out at the same spot, okay? So if you notice, how does that show itself in P of x? It shows it by the function just touches there, okay? It touches. It's what's the geometry word for touching? Oh, you didn't learn Latin?
Intersecting.
My kids learned Latin, and so when they were in the car, they would say, "Dad, he's tangenting me," and I'd say, "Quit tangenting your sister." True story. No, it's not. It's all made up. If you were speaking Latin, though, tangent means touch. So it's tangenting the 0. Not crossing it, just tangenting it. Okay? So we wrote 3 twice. If that is true, we could write the factored form of this function. What are we going to have to do? Does that make sense? Squared. To me, this is very valuable information. As a mathematician, I can look at this graph and it explains a lot of things. It would be nice if the graph would explain a lot of things to you too, but sometimes it doesn't. I was reading in the paper today about a player that used to play for the Vikings, Cordell Patterson. Anybody ever heard of him? He was a number 1 draft choice by the Vikings. 4 years he played for the Vikings. They tried him as a wide receiver. They tried him as a kick returner. I mean, he returned like 4... What?
So he's a Patriot, right?
Yeah, that's, you know the end of the story. So he was a kick returner, returned like 5 kickoffs for touchdowns, extremely fast. The Vikings didn't know how to use him. So for 4 years he languished there. They cut him or something. He shows up at the Patriots, and Bill Belichick, arguably the best NFL coach ever, says, "I know how to use this guy." He lines him up in the backfield. He puts him out as a slot back. He puts him out as a wide receiver. The guy has caught more passes this year than he caught in the first 4 years of his existence. Okay, he figured it out. I would love it if you guys would figure out math too. But you know what? It takes some, like, I'm not going to say effort because that makes it sound like you're not trying. It takes some affirmations. There you go. But the thing that is really cool about it is it helps you, like, love the game. Bill Belichick loves the game of NFL football. The rest of us just, like, watch it. I mean, you listen to some of those color commentaries. Chris Collinsworth, the guy knows the NFL. I mean, he can say, "Oh, it looks like it's going to be a pass to the wide receiver out on the left-hand end." Sure enough, that's what it is. Tony Romo has developed into a superb commentator. Why? Because they understand the game. If you can look at this graph and you can say, "This is so cool, I understand things about this." Over here on the right-hand end, what's happening? It's going up. Over here on the left-hand end, what's happening? It's going up. What do you know must be true then if it's going up on both ends? 1, it's got a positive coefficient, and 2, it must be to an even power. Okay? If it's to an even power, it must have 2, 4, 6, 8, 10, some even number of roots. How many does it have? 1, 2. Well, if it's got 3, one of those must appear twice. Okay, so all of the rules kind of come out and help and reinforce each other to help you understand what's happening. Now recall, all of this is related not to the whole function f, but to the p part, to the numerator part of the function. So we know that this must in part be how the numerator looks. Now, there may be more stuff going on, but that is for sure part of what's going on. Let's look at the denominator part. Oops, where are we? Oh, I know, I got to go here. So that's the numerator part. Can the graph be used to determine the zeros of the main function? Yes, because a zero of the numerator, here's your explanation you should write down in your notes. A zero of the numerator is a zero of the function. How do we put zeros on our graph? We make a little dot, right? And we're either going to go through or touch that dot. Next, here is the graph of the denominator of our function. So let's do q of x. Q of x is going to be our zeros of the denominator are 2 letters. What are they? Vertical asymptotes. Okay, so let's look at q of x, and where are those zeros? There's a 0 at -2. +1 and +4. Correct? So how would we write the factored form of the numerator? See if the person sitting next to you can do it right. I'm going to do it down here so that you can't see it. I want to show you my work. Is that what you wrote? X plus 2, x plus 1, x minus 1, x minus 4? Now, what's interesting about this graph is that we can count the number of turning points. How many turning points are there? Well, there's one between -2 and 1, or -1. There's one between -1 and +1. And there's one between +3 and +4. Therefore, there are 3 turning points, which means the power of our graph has to be at least 1 more, 4, right? Is it 4? Do we have 4 factors? Now here's the thing that's different, is that it has to be at least 4, but it also has to have an even number of roots. Why? Because 1, 2, 3, 4, it's got 4 for sure. If this 4 over here appears once, so I cross the river, okay? In order for me to end up on this side of the river, I have to cross 2 more times, right? So I either cross once, or I cross 3 times, or I cross 5 times, or I cross 7 times, right? Everybody agree? Every time you cross the river, it's going to be an odd number of roots. So if any of those appear twice, they have to actually appear 3 times. Now, we don't know that for a fact yet because there's some other stuff going on. So we wrote so let's write, part A. Describe the zeros of this polynomial. Where are they? And which are turning, we didn't do that up here. Up here, this one here, it's important, and they didn't even tell us it. It's important that this one is a turning point. Let's look at the graph just to make sure. On the graph, this 3 is a turning point also. So a root that is a turning point is even. In other words, it appears twice, 4 times, 6 times, 8 times. Got it? So in this case, it asks, are any of these roots here, too far. Are any of these roots here turning points? This is a root. Nope, not a turning point. This is a root. Nope, not a turning point. This is a root. Nope, not a turning point. So are any of them turning points? Nope. So are any of them an even number of roots? Nope. They're all odd. Then it says, using the graph of P and Q, determine all the zeros, all the vertical asymptotes of the functions. Let's go back to our graph here. And let's modify this graph. Let's do the vertical asymptotes first. There's a vertical asymptote I'm in the denominator, right? -2. X equals -2. X equals -1. X equals +1. X equals +4. For any of them, do we write the word twice? No, because none of them are turning points. Okay? Then let's do zeros. I'm going to use green for my zeros. So I should have done this in green, shouldn't have I? Okay, so I put a dot at 0. I put a dot at 2. And I put a dot at 3 and write the word twice. Do you now see that when I sketched my graph here at the beginning of the lesson, I was not as precise as I should have been, right? What should have I done here on my purple? Gone down through this root, come back up and touch the graph, and then back down. Why couldn't have I come here, down, touch the graph, gone back up and gone down here? Because my asymptote, right? I had to switch directions at my asymptote. So let's modify our function so that it is correct. So this section here, we were wrong. We should have gone like this. Okay? So we just spent a lot of time figuring out that one little section of our original graph. Why did we have to do it? Because when we graphed it, we didn't show it real well in this section of the graph. Our scaling didn't allow us to see what was happening in that section of the graph. Okay. One more thing. page 267. One more thing in this lesson. So now they took our graph and they stretched it out here so that they went from negative 100 to positive 100, and they showed that graph stretched out. Well, when they did, all that monkey business that we were doing before happens way in this section of the graph. All of that stuff that we just did, all of those roots that we found, happened way in here. So that they could show us one really, really, really important thing. Over here on the left-hand end of the graph, as we got closer and closer to infinity, did we get closer and closer to 0? What did we get closer and closer to? 1, right? As we went over here on the positive side, as we got closer and closer to infinity, we got closer and closer to 1. Okay? Let's look at our notes. Well, come on, come on. Here it is. Which rule for the end behavior are we following here? Numerator littler than the denominator? Nope. Numerator power the same as the denominator, right? If that is true, what do we look at? The coefficients of the numerator, the coefficients of the denominator. So now when we look at our function, we have to make sure two things are true. Oops. Two things are true. Thing one, we have as many powers in the numerator. How many do we have? As we do in the denominator. Is it true? Yeah, it's true. If this number is 6, that means one of these appeared at least twice. But if this number is 6, this number also has to be 6. Why is that? Because our end behavior is 1. How do we write that? The limit as x approaches infinity of f of x is 1. The limit as x approaches negative infinity of f of x is, what number do we get closer and closer to? 1. So where we wrote a question mark here before, when we zoomed out, or the end behavior, f of x equals 1. So where we had written 0 before, we weren't right. Okay, our graph was off a little bit. How do we know that? Because when we zoom out, the way you find that end behavior, zoom out and find out where you end up. There are 2 test questions on end behavior. Password. Oh, you didn't give us the password. Oh, please. All right. Does it make sense that the end behavior is 1? I mean, by looking at the graph here. Right? It stretches out all the way to 1. When you stretch out, you compact the middle part. One more thing left to do on this graph. Oh, let's answer this question. Based on the graph, what can you say about the zeros and asymptotes of f? Well, one of the things you can say is there are no other zeros or asymptotes of our graph. Those are the only ones that appear, right? We zoomed out far enough to see nothing happens out of the ordinary beyond where we were before. There are no more. But the other thing we can say is that there are as many zeros as there are asymptotes. How do we know that? Because the end behavior is at a number other than 0. As many zeros as asymptotes. Or at least the even oddness works out the same. What do you know about the function f at infinity? It must be, f of x must be 1. All right. We still need one more section of the graph in order to draw the whole graph, and that is this section right here. Next lesson, let's do that section of the graph. Page 263. (19b). When analyzing a function, which 3 graphs can help you? The graph of the function, that'll give you some help. What other 2 graphs will help you? Graph of the numerator and the graph of the denominator. All 3 of those will help you figure out your function. Let's enter these 2 functions into Desmos so that we can look at the graph. So, here's my graph of P, here's my graph of Q. I'm going to get them on the same scale that we had in lesson 19A so that you can see that they're the same graphs. The scale was, oh, I know, it's over here. The scale was, y went from 0 to 80, and x went from -3 to +4. 0 to 80, -3 to +4. Oops, I didn't. It must have been more than -15. Let's try -30 to +80. And I still need to go out just a little bit more. It must have been farther than 4. Okay, so there's our 2 graphs. The graph of the numerator is in red. The graph of the denominator is in blue. And if you look back a few pages, those 2 graphs match, right? Do you have them graphed on your Desmos? Please. Pretty pleased with sugar on top? I've been thinking about that. One of the things that folks think is that doing the homework helps them learn. Doing the homework helps you learn only if you don't use the helps that are on the homework, okay? If you count on the homework helps to get through the assignments, you're only using the hints to get, you're doing the homework without learning the stuff. You gotta learn in order to succeed. Okay, so we've got those 2 graphs. It says graph those 2 functions, and then let's turn those 2 off and graph the composite function. Now, the easiest way to do the composite function is just copy the numerator and put it into the function, copy the denominator and put it into the function. And if you notice, now we can see, well, for one thing, we can't see that our horizontal asymptote is over here at 1 and negative 1, but we can see that section of the graph that we were missing is down here, and in fact, we can see that it peaks at negative 29.626. That's not where we are right now. Where we are right now is back on page 264. What do you know about this function? This is where you need to start putting stuff together. 1, I know the zeros of the denominator are at these vertical asymptotes. 2, I know there is one crossing at 0. 3, I know there are a crossing and a touch between positive 1 and positive 4. Part B, are any of these zeros turning points? Yes, they are. If you look at our graph, this one right here is a turning point. Here's how to find so we zoomed out to find end behavior. Let's see here. Pardon? Zoom in vertically to find turning points that are roots. So I'm going to go on my graph and I'm going to change my y from being from negative 49 to positive 82 to negative 1 to positive 1. And when I do, that still isn't zoomed in enough. If you notice here, look at how close this turning point is. We can see there is one, but it's at 0.01. So let's change our graph even, let's zoom in even farther. Negative 0.01 to positive 0.01. Now when we do it, we can see, oh yeah, that's a definite turning point. But look at how close that turning point is to the relative minimum here. This thing only goes 1/100th below the graph. Well, that's why we couldn't see it at regular scale. It barely went below the line. It crossed the river, but it didn't cross it very far. Okay? So we really zoomed in order to see that. So if you want to find turning points that are roots, zoom in until you can see that they are. So are any of these zeros turning points? Where were we? It's not on.
Page 264.
264. Are any of these zeros turning points? Yes, the one that was at x equals 3. Then it says, consider the interval from negative 2 to negative 1. So on our graph, we're back here from negative 2 to negative 1. At this scale, we don't have a clue what's happening because we zoomed way in. Let's make it so that we're at a regular scale. Let's go from negative 10 to positive 10. And let's go from negative 10 to, oops, that's negative 108. Negative 10 to positive 10. The reason why I want to go in that section there is that's the default when you graph using TI-84, right? Isn't it? Negative 10, or is it negative 5? That's 10, isn't it? What's the default on a negative 10 to positive 10? So that is pretty close to that scale that we had before, right? One of the things that you kind of notice at this scale is, doesn't it appear like our graph is kind of rising over here on the right-hand end? We know we end out at positive 1, but it appears as though we're coming at positive 1 from the bottom, doesn't it? At this scale? That'll be interesting to try to find out. But the part that they're talking about is what happens from negative 1 to negative 2. That is where we want to focus our attention next. Number 3. Oops. For any x in the interval from negative 2 to negative 1, what is the sign of the numerator? So let's go back here and choose a number between negative 1 and negative 2. I like to choose the one right in the middle. So negative 1.5. If we raise that number to the 4th power, what do we get? Positive. If we raise it to the 2nd power, what do we get? So these two numbers are both positive, right? If we raise it to the 3rd power, what do we get? Negative. If we raise it to the 1st power, what do we get? Negative. What's a negative negative? And what's a positive negative negative? Positive, right? So we have a positive, plus a positive, plus a positive, plus a positive. What's going to be true about our numerator? It's positive. Let's put it on our paper. So for the interval from negative 1, negative 2, oh, I should ask, does everybody understand the notation I just used? I'm using interval notation, right? That was somebody in Menominee that had a question about that. But you understand it now, right? Mm-hmm. Okay. For that interval, f of x, we know the numerator's sign, we only care about the sign, is positive. So what's the next question asked? For that interval, what is the sign of the denominator? So let's go back in our lesson to the denominator. Okay, so we're choosing a number between negative 2 and negative 1, negative 1.5, right? Okay, negative 1.5 to the 4th, positive. Positive, that's already positive. So the even ones are all positive, correct? Except this one is multiplied by a negative number. So that makes this term right here negative, right? So we have a positive plus a negative plus a positive. Let's go to the other ones. If this is a negative number to a power, this one is going to be negative, but a negative negative is a positive, right? And this one here is going to also be a negative. So now we need to do a little bit of math here to find out what the sign of the denominator is. Because we have a positive number, then a positive number, then a negative number, then another negative number, and then a positive number. So if you're balancing your checkbook and you have a deposit plus another deposit plus another deposit, and then you have 2 withdrawals, do you know how much money you have in the bank? No, because you need to know how much those 2 withdrawals were. Whereas before, if all we were doing was adding money each time, we had a deposit plus a deposit plus a deposit plus a deposit, we better have, unless somebody stole our money from the bank, we better have money in the bank. So now we need to look at what value do we end up with. Well, negative 1.5 to the 4th is not going to be very big, right? Negative 1.5 to the 4th.
Negative 5.06.
Okay. Then we do the next term, which is negative 1.5 cubed times negative 2. And we get 6.75. So right now, so far, you could say we're above 0, right? We're positive. Let's do the next term. Negative 1.5 squared times 9. Oops. Clear. I have to put it in parentheses. Negative 1.5 squared. I screwed up on that first one too. I didn't put the negative sign here. This is already positive here. That first one should be positive 5.06. Negative 1.5 squared is 2.25 times negative 9. Is negative 20.25. Okay, the next term plus 2 times negative 1.5 is negative 3, right? And then plus 8. So here's all our terms all added together. Now we could just go through our polynomial and find those values. But if you notice, we're up about 11, subtract 20, subtract 3 more, then add 8. Where are we going to end up? Negative something. We don't need to know exactly what it is. All we need to know is that it's going to be negative. Okay? So the sign of our denominator is negative. If that is true, our function is going to be below 0. So for that interval, what is the sign of f of x? The sign of f of x is negative, so we're going to be below 0. If that is true, and there is only one turning point in that interval, does that make it going up or going down? Okay, so I'm approaching the river from the bottom. If I don't cross the river, I must turn around and go back down. What does that make the spot where I turned around? A local maximum, right? So on our graph, here's where we are. For this interval, should we go this way or this way? Should go down, right? And sure enough, there is our graph. By hand, draw a graph that shows all the zeros, asymptotes, holes, maxima, and minima. So I'm going to scroll back in my notes to my graph here. And now I'm going to put in the missing section of my graph right here. And my local minima is at negative 1 point something and negative 29 point something. There was a local minimum over here too. Don't recall what it was. We can find its address though pretty easily. 2.34 negative 0.01. So now we have sketched our graph. Why is that so important? In calculus, we spend tons of time analyzing graphs of functions. We do it a lot. Why do we do it? Because it helps us understand what's happening to the function. What does the function do for us? It tells us information that's really important to know. Like, for instance, if you are building cars and you're selling fewer cars than you're making, no matter what President Trump says, you gotta switch what you're doing. Otherwise, you are going to be the Sears of the automotive world. What happened to Sears?
They suck.
They were big and they got small in a hurry because they didn't change. So now, President Trump's right. We got to do something. Why is GM quitting making small cars? Nobody's buying them. What could they do to get people to buy them? Lower the price. Why can't they lower the price? Because they're probably already not making very much money on little cars. They're making scads of money on SUVs. Why? Because everybody wants an SUV. Raise your hand if you drive a car. Oh, really? Lots of people drive a car. Raise your hand if you drive a car made by Honda, Toyota, one of those foreign car makers. Okay, so about half of our hands are going up for that. Those car companies are still making cars because people are still buying those cars. So then President Trump says, dude, and he's talking to that lady that's the head of GM. He says, dude, you gotta quit making cars in China. Do you know why GM is making cars in China?
It's cheaper for them.
It's cheaper for them to make them for the people that are buying them. Last quarter, GM sold more cars in China than any other place in the world, including the United States. So why the heck should they make cars in the United States, ship them over to China, when the Chinese are going to buy them, and then why don't we just make them in China? That will help our profits, which will help us be able to support workers here in the United States. So GM, they didn't close those plants for nothing. Why did they close those plants? Those 4 plants they closed. They're going to explore new areas, like 2 things. What's the big buzzwords in cars?
Self-driving cars.
Self-driving and alternate fuel. Yeah. Those are the ways they are going to go. They couldn't make those cars in those factories because those factories were built to have people building cars. Automation is going to help them build cars. Now you may say, well, that's going to put people out of work. They aren't going to be in the business of making cars because the robots are. Do you know anybody who has a job whose job it is to fix robots? It's huge. Nestle here in Eau Claire has like 15 people whose job it is to keep the machines running, the robots running. Just think how many people there are going to need in those factories to keep the robots running, to program the robots what to do. I mean, that's what people are going into, okay? Can you do that just fresh out of high school? Here's a robot, teach it what to do. Oh, okay, yeah, I can do that. No, you're going to need training in order to do that. All of those things are related to calculus, to mathematical solutions. GM made that decision based on mathematical data. Page 19C, new topic. We'll take our break. Jake, was it you or was it Nick that wanted to retake test 3? You did, and you're going to do it next week, right?
Yeah, that's all right.
Yeah, that's fine.
It's about 16. 16. What's yours? I just got like a 22.
Weren't you here the day that we did the
42 kills.
Yeah.
Here's the test. See which things you got wrong on there. That's the test that we took. You wanted to look and see if you could remember what things.
Sure.
Dude, I'm so tired, bro.
I've got yours downstairs. You could look at it.
Yeah.
Yeah, you were like sitting on there completely.
I was like,
Who's the king in your game right now? Toy Town? Oh, okay. We're not the same.
no, I just like, my brother called me this morning at 6:30. He's like, yeah, I need you to go show me driving. I was like, oh, shit.
Why do you have to do
I was like,
it?
why are you calling me? It's so late.
Like, I was able to do tests and see what I got wrong.
Now I'm like super cold.
Yeah, like, make sure you sweat during the driveway.
Yeah, exactly.
I feel you.
Just watch dude kill himself.
Once this class got me stressed out. This is maybe the worst class is so much stressing me out. I enjoy reading it, but there's so much to do. I have this semester of things.
I don't even know these. Right, yeah.
I'm getting into just I don't really know that much.
You're just not gonna do.
Oh my gosh, how did he even get me? That's 17.6 right there.
Yeah.
Such a weird temperature. Why would those
Who's your king right now?
Miss Murder. That's yours right now?
Oh.
shoot, I'm supposed to order some Chinese food. Yeah, I gotta look at what food I want to order.
Priorities.
Actually,
Second one.
menu. Chicken, fried rice and lo mein. That's what I want. Chicken fried rice. Chicken lo mein.
No matter what.
So I want egg. You just give me this. Don't take pics. Take pictures. Wait.
So,
Shows.
definitely not looking, not liking the way it looks.
Yeah, dude, that looks really rough. That's okay.
Oops.
Dude, I would feel that time. Be sitting next to me.
Oh, come on. Let's go, man.
She's one of those people who's like, really had it.
Let's get each other through this.
You're like, Kevin, you think that's the next test?
This bit, I don't like whatever it is.
Whoa, what is that?
I wasn't paying attention.
That's our next test.
Oh.
Like,
Man. That's. You ever circled someone?
I take mine test home.
Basically what just happened in class. That's why I sit down. I definitely want to see what I don't have it. Yeah, I know where you're going. I'm in the same thing. I'm never getting this. You can hand me the next.
Oh, that's 3 tests? Okay. Test 2 you need, huh? I might not have it on me then.
That's okay.
You can come down to my office and get your copy, okay? Look at it, comment.
Right, you want me to do that right in class?
Sure, you could do that after class. All right. 19C. Take out your notes and let's draw a picture of our function machine. I don't know how exactly to draw my function machine, so I'm going to draw it like a, I don't know, I'll make it kind of like a copying machine. So you got a copying machine thing that looks like this, and then it's got some parts in it, and maybe a couple downward parts, I don't know. But somehow I've got this. This is my function machine. Okay? On this side of my function machine, these are my inputs. On input. On this side of the machine is my output. Now, if we were going to use function notation to just, oh, you can't see it. Just say it. Kevin, I can't see your picture. Now I can. So if we were going to describe this using math, we would say right? That's how we would do it. The function of the input is equal to the output. So the machine is going to take our input and make it into an output. Now on our machine, there are 3 dials. I should do them in different colors. My 3 dials are the input shift, the output shift, and the scaling factor. So this one either stretches it out or shrinks it up, correct? This one moves the graph left or moves the graph right. And this one moves the graph up or moves the graph down. Everybody agree with those three things? Okay? Now, we learned that when we are going to adjust our machine, the order of adjustment was to shift the output last and to scale first and to change the input second. Okay? Everybody agree with those three things? That's the order we do them. The reason that's important is here is a function. And it's got the two knobs, A and B. Based on your experience with scaling graphs, can you determine what will happen to the graph of f as A changes? Where is A in connection with our variable? It's a coefficient, correct? What do coefficients do? Stretch it out, correct? The coefficient B will also change our graph, but if you notice, it's connected to the denominator of our function. It's going to have a different effect on our graph. Consider the fictitious drug called codrazine. The concentration of codrazine is measured in nanograms per milliliter, is modeled by the function f of t is AT/BT squared plus 1. T is the number of hours. A and B are positive parameters. Let's go to Desmos and let's graph 19C. Oh man, I didn't ever graph it. Oh, yes, I'll have to do it now then. Okay, codrazine. I don't know why they say F, but we'll use F as a function of T. I would have said the C of T, but anyway. Equals a fraction AT over B T to the second come on now. Plus 1. Now, before we can still add sliders, but the thing that we have to make sure is that our slider starts at 0 and goes up from there. And we can try it up to 10. And our other slider goes from 0 and it's going to go up to 10 also. Okay? So there's our function. And notice A and B are parameters, and the function can figure that out right away. How does it know F isn't the a parameter? Well, because it doesn't. It's always our function. How does it know T is not a parameter? Because T is usually one of our choices, right? Time is a very common thing that we're going to graph. So it says A and B. Now, let's see what happens when I change B. So I'm gonna let B increase and decrease. If you notice, what's happening is all of a sudden it goes off the screen over to the left-hand side when it gets really, really small. So I'm going to slow it down here, and I'm going to just move gradually this way. Do you see what happens to B? The peak was here, and now if I make it just a little bit smaller, like 0.01, the peak moved way over sideways. Okay? Let's get B to be about there, and let's play around with A. What do you see happening when A gets bigger or smaller? The peak goes straight up and down. Page 268. In question 1, you thought of the effect of A on the graph. What did A do? A made it go vertically up and down. It stretched it out. It was the coefficient of stretch. What does B do? Well, B moves the peak left and right. It's acting like an input shift. According to our directions, which one should we play around with? Which knob should we play around with first? The input shift should go.
So it's the output shift, right?
It's the input shift goes before. We aren't worried about the output shift right now. We're worrying about those two values there. Well, if you look at our graph, it doesn't matter how high you go until you look at how far left and right you go. So let's look here. Number 3. Assume the concentration of cordrazine peaks 1.2 hours after injection. Right now, it is not at 1.2 hours. We need to make it go a little bit more to get to 1.2 hours. A little bit smaller. I'm going to have to adjust my A down a little bit so it doesn't go off the graph. Okay. So now my peak is at 1.04. Okay, I make it so my peak is at 1.2. There it is, 1.2 is my peak. So B is going to be 0.76. Now, I was working with some students in the other section, and they were doing this assignment 19.C, and they had some issues with it, and that's because it was seeming like it was really persnickety. And I don't disagree with them. So let's look here at 19.C. Let's see, 19, all chapters. 19C. And let's do 19C1. So if you notice here, it gives us our drug, and it tells us that A, let's go to the next question, because that's the one that, okay, so here it says, the fictitious drug hydraline reaches a maximum concentration at 23 minutes. So if you recall, the other day, I told you you have to be able to change 23 minutes into a decimal. So 23 divided by 60 gives us 0.383. So we need to have our graph go through the 0.383. I'm going to make another graph here. Oops. 19.C number 2. Okay, so f of t is the fraction a t over b t squared plus 1. Add those sliders. And we want to have this peak set so that it's at 0.38. So instead of being 1, it's going to be 0.38. Well, to do that, we have to make a smaller than 1. Let's try 0.1. I'm sorry, b we have to make 0.1. I'm going to make my peak bigger so that we can see it. B right now is at 0.9, or the first coordinate is at 0.953, so our B value is a little bit too big. If I make it 0.5, my B value is at 1.4. Oops, I'm going the wrong direction, aren't I? Make B 2. Now I'm going the right direction. My peak is at 0.7, so B's got to be a little bit bigger. 3. 0.23, so that's not 0.209. We want to go to 0.38, so 23 is too big. Try 18. So really what you're doing is you're playing around with this slider until you get to the right value. On here, we are now at the right value of B because we wanted it to be 1.2. Oh, how did that switch? I thought it was at 1.2 just as when we left this graph. 1.15. $1.125. $1.2. So if B is 1, our cordrazine will peak at 1.3 hours. Then it says you want it to have a concentration of 3.2. So what we're shooting for is so that our graph goes through the point 1.2, comma, 3.2. I'm going to change the color of that point so that it's a different color. Okay, so we want it to go through that point right there, over 1.2, up 3.2. As we increase our graph here for A, our B is has to shift forward. There it is. 1.29. It's a little bit too big. Oops, we just passed it. So you get the peak so that it's at 1.2, and then you can adjust A up and down so it goes through that point. Now if you notice, it appears as though those two values are about right. So what we're saying then is that if this goes through that point, A is 5.6 and B is 0.76. So you notice it's kind of like I was showing you on that machine. You're adjusting dials so that you go through a certain point. And that's what you're trying to do with this function machine in this lesson 2.68. So if it goes through this point, the next question they ask is, at what time do you find the half-life? Well, if the drug peaks at 3.2, what would the half-life be? Half of 3.2 is 1.6. Where does it reach 1.6? At 4.299 hours. So what is the half-life? Well, it's the difference between 1.2 and 4.2, which is about 3 hours. So every 3 hours, it loses half its potency. So what the scientists who work with these chemicals try to do is adjust these inputs, scaling factors, outputs, so that the drug does exactly what they need it to do. Like, for instance, let's take a drug that relieves pain. What parameters would you want to have to be true for that pain-relieving drug? You have a splitting headache.
It acts quickly.
Work fast, right? Okay. Reach an effective level quickly. What else would you like it to do? What do all of the pain relievers advertise? You only have to take it
Once a day.
once a day, right? So you want it to last a long time. And probably 3, you don't want it to kill you. Now, you don't even think about that, right? But I know of 2 famous singers who could have used a little help with that thing. Who were the 2 singers that died because their pain relievers were too strong?
Prince.
Prince and Michael Jackson both died. And I'm not so sure if Elvis didn't die also because his pain reliever was too strong. Okay? None of those guys wanted to die. They didn't take the drug because they wanted to die. They took the drug because their pain was a lot. Are you disagreeing with me, Jess? You aren't.
Well, with Prince, he got flown in and was given medication for an overdose, and he took more and then overdose.
And you're right. But what I'm saying is he didn't take more drug. Okay, I think what you're saying is, like, was he taking it because he was addicted?
Yeah.
What I was saying was he wasn't taking it because he wanted to die.
Okay.
That's what I was
So that's what
constantly.
I've heard, because he was flown into, I think, Chicago or something, and was given medication to stop the drug.
To stop the drug. Yeah, what do they call it? Narcan?
Narcan.
Narcan, yeah. I don't believe any of those 3 guys wanted to die. I honestly don't believe that. I think they were thinking they could get a certain level of pain relief and still be able to live. That's what I think. Okay. So the scientists want to adjust those things so that people don't die. Page. We're skipping 19D, and we're going to page chapter 20. Chapter 20. Oh, I was just there. Suppose you are studying the spread of an infectious disease through some population. Now, the one they talk about is squirrels. The one that I like to talk about is CWD, which stands for?
Chronic wasting disease.
Why is that a good one to talk about in this area?
Deer population.
The deer population has chronic wasting disease. What is that? Their brains have some kind of a infection that causes their brain to deteriorate and go away to nothing. How did it happen? Somehow a germ got on the other side of the blood brain barrier, and not drug, some kind of a virus or something got on the other side. I had a friend who died of, they don't call it CWD in people. They don't call it mad cow disease in people. They call it
Lewy bodies.
Creutzfeldt is the last word. What?
Is it? Maybe I'm wrong. I thought one of those Lewy bodies, or no?
That's one of them, yeah. But the other one is Creutzfeldt disease. I don't know. Creutzfeldt is the last word of it. She died of it. And here's the end of the story, and then we'll work back to the beginning. A couple years ago, her son was getting married in Boston, and so she flew out with her husband on July 3rd. I saw her in church the previous week, and he had bought one of those I was going to say strollers, walkers that you could sit in, because he figured she could like wheel it around their house. Well, by the time they got it, she was already so weak she couldn't be wheeled around the house. So when I saw her in church, she was sitting on it and he was wheeling her because they couldn't afford to buy a wheelchair. And we had already wasted all this money buying this walker. Well, anyway, so then the next week they flew out to Boston to go to their son's wedding, and there's pictures of them on Facebook. And then she came back and she died that week. So, I mean, the end of the story was just like that. Okay, backtrack. 50 years. Sometime in the previous 50 years, she had eaten something that was infected with brain material from an animal that had CWD or mad cow disease or something. Back in the day, they used to make bloodwurst or brainwurst. Okay, they used to take brains and make it into, and people would eat it. Now I know her dad. Her dad was one of my teachers, and he was one of those crazy Germans who, oh, that's just great tasting stuff. And I'm like, dude, it's brain. I'm not going to eat it. Okay? Well, she probably did, got infected. 50 years later, she died. What does that have to do with chronic wasting disease? Well, chronic wasting disease right now has been found. Was it in Dunn County or was it in Eau Claire County? Someplace.
Dunn, I'm pretty sure.
Where?
Dunn, and then it's like a 50-mile radius that they kind of protect.
Right. So they found it there, so they made a rule that within 50 miles, you couldn't...
Bait deer.
Okay. No, what's the scoop with baiting deer? Well, you get deer that they come and they eat that corn that you have piled up there. You're forcing the deer to come closer and closer to each other, and so you're forcing these deer that are sick to come in contact with deer that are not sick, okay? Kind of like people. Why do we have colds in the winter? We're inside, and it's easier to spread disease when you're inside. Now, I can tell you this. I was reading in the Parade magazine, I can't remember, Ask Marilyn. She said, doesn't matter what you touch. You can touch anything that's infected. It's what you don't touch once you have it on your hand. Where should your hands never touch? Your face. Yeah. If you can keep from touching your face, you will not get sick. Okay, let's go back to the squirrels that they're talking about in our lesson. What's that, Matt?
Wait, if I eat a deer that's sick with that, will I get weird too?
No.
Well, that's... here's the thing. Here's the thing. Nobody wants to run that experiment.
They've been
It's one of those, I volunteer. What were you saying?
They claim that you can't get any diseases from CWD infected deer. That's like an article I read from the DNR.
Yeah.
But
The other article that was go to the internet and check it out. In about 2006, some researchers made the claim that opioids are not addictive, and so from 2006 to 2015, doctors were prescribing opioids like candy. They aren't addictive.
Yeah,
Well,
but
then about 2015, the doctor said, I've been noticing all of my patients that I prescribe opioids to, they get crazy and start wanting more and more opioids. And I'm like, well, you shouldn't have any more opioids. Yeah, but I really, really, really feel like I need them. Do you know what that thing is where you really, really, really feel like you need something? Yeah. It's an addiction. Okay. Like Chinese food. Okay, so here we go. Let C of P be the contact rate, which measures the number of squirrels per day that are exposed to the disease. Additionally, let's assume that the squirrel population is given by P of T, where T is measured in weeks. So here they show the graph of C of P and P of T. We're going to give a function C of P of T. c as a function of p as a function of t. In other words, we're going to get an input and use that input on another machine. This is a composite function. Let's go to our notes. C as a function of p as a function of t could also be written as c circle p of t. That's a way to write that function. Here's a way to think about that function. Here is our time axis. Here is our p-axis. And on that graph, this is p of t. So on that graph, we've got a graph that goes like this. 0, 300, and it's got a slope of about, I don't know, by the time you get to 4, does 4 look like it's up at 400 yet? No. 5 is though, huh? So over 5, up 400. Okay, so our inputs, they show going from 0 to 7. Now, our other function, this is p, and so I'm going to kind of try to show it as three-dimensional. So this axis is going up into the air. Can you understand what I'm trying to show you? So you've got the p-axis, and this is the c-axis. So it's kind of going up into the air. Well, if you notice, we don't even have to get started at 0 because the first spot that we're going to be across the axis here is at 300. So even though they show this graph starting at 0, it goes all the way over to 2,000. I mean, this graph is going up really, really fast. How fast is it going up? Kind of like this. I don't know how to show you 3 dimensions on a 2-dimensional piece of paper. I've got some pegboard at home that I'm going to make the graph. But do you understand what I'm trying to show you? Is that when you're doing a composite function like this, you've got your base function, the inside function, the axes are going this way. The output of this function is the input of the other function. That's why I'm trying to show you those two, three-dimensionally. So, if that is true, here is the c as a function of p is 6p over p plus 1,000. This is indeed a what kind of function? Rational. Where is the asymptote of the denominator? P can't be negative 1,000, right? Negative 1,000. So there is a vertical asymptote at negative 1,000. Where does it cross the axis? That's what our p of the our 0 of the numerator is. Where does it cross it? At 0, right? And what is the maximum value at infinity? Those two powers are the same. If the powers are the same, what do we go by? The coefficients. 6 divided by 1 is 6. So if you look at that graph of P, does it look like it's going to have an asymptote here at 6 if we go farther and farther along? Well, there's 1, 2, 3, 4, 5, 6. Does it look like it's getting closer and closer to 6? Okay. That's our P function. Here is our P of t function. What kind of a function is it? Trick question. What kind of a function is this? Shouldn't have to ask.
Linear.
Linear. You could tell, first degree, no fraction, everything's, what's the intercept? 300, what's the slope? 20, right? Which kind of goes along with what we had said here, over 5, up 400. So it looks like for every 5 you go over, you go up 100, which would be a slope of 20, right? Now it says, find a formula for C as a function of P as a function of T. Here's how you do composite functions. Give the structure of the outside function. So in other words, no variables. So, C of is something times 6 over something plus
1,000.
1,000. Step 2. Substitute in the initial function. Okay? So we know this is our base function over here. We're going to run our value through our initial function in order to put it into our base function over here. Now we're going to combine those two machines into one. The way we do it is wherever we see P in our original function, we want it to be T, right? And so we're going to take 6 times 300 plus 20T. That's going to be our numerator. What's going to be the denominator? 300 plus 20T. So, now that that's written that way, let's go back and let's see if we can simplify it. C as a function of P as a function of T is. How do you simplify this numerator? Does that make sense? 1,800
It's 122.
plus 120T. So I took the 6 times the 300 and I take the 6 times the 20. Over
1,300.
Does that make sense to everybody? So now when we graph this function, we're going to go through the point 120t equals negative 1800. So negative 1800 divided by 120 is, we're going to have a 0 at t equals negative 15. We're going to have a 0 in the denominator. 20t equals negative 1300. So negative 1300 divided by 20 is, we're going to have a vertical asymptote at negative 65. So our graph is going to go like this. And where is it going to end behavior at? Y, or t, c of t. C equals 120 divided by 20?
6.
6. So it says, as t increases from 0, so we're just talking about the interval from 0 here to 10. Well, from 0, it's going to have some kind of an intercept here. Does anybody know what value that's going to be? If t is 0, what are you going to end up with? 1800 divided by 1300. It'll be up 1.38, right? Over at 10, well, if you look at your formula here, at 10, the numerator will be 600, right? And the denominator will be 1500. Is that right? Parentheses, 1800 plus 120 times 10 divided by parentheses 20 times 10 plus 1300. And we get 2. That was a lot of work for 2, wasn't it?
You're just plugging in.
I just plugged in t as 10 in each one of those spots. Every place where t came up, I just put in 10. So as t goes in that part, what happens to c of p of t? It keeps on getting bigger. But when t is very, very large, another test question, t is very, very large, it gets closer and closer to 6. Good. Okay, next one. So it's another composite function. F of x is 1 over x. G of x is x plus 4 squared. Here, the domain x does not equal
6.
6. No, 0, right? If you put 0 in, it won't work. The range is from negative infinity to positive infinity. Oops, I should make these parentheses. Sorry about that. Over here, the domain is from negative infinity to positive infinity because you can put any value in for x. And our range is going to be from 0 to positive infinity. Why can't it be negative? Because when you square a number,
It's going to be positive.
it's always positive. So if we look at our graphs here, let's see here. 20.A composite function. So if we look at our function, oh, they don't give us the choices there. But anyway, on the next page it says fill in the domain and the range, which we just did. And then it says two more things. What happens if you composite from g of f of x and compare it to f of g of x? So first off, let's draw the two axes. So this is x, and this is f. And then let's draw the other one. So this is x, and this is g. If we draw f of x on here, our graph looks like this. If we draw our g of x graph, we have x plus 4 squared. It's going to go, let's see, 0 plus 4. We're going to be shifted forward 2. No, backward 2. I got to make sure. Y equals x plus 4 squared. Yep, it's shifted back 4. So our graph is going to be back 4 and a parabola. Then it says, now take that function and turn it sideways. So this is now the g-axis. So we're going to make this function onto our g onto this function. Well, one of the things that you notice is, actually we should have drawn the other part of it, and that is that it went like this down here in the other axis, right? It was like that down there. Now it's saying, what happens when you compose that function? And over here, what happens when you compose this function onto the f-axis? How does it look? Well, let's do it. This first one we start with, our base function is g of something. Over on this side, our function is f of something, because this is where we're going to end up. That's our base function. What is our form of g? Our form of g is to take something, add 4 to it, and square it. Our form of f is to take 1 and divide it by something. Well, let's put in our input function in each of those places. F of x, g of x. Our f of x is 1 over x. Our g of x is x plus 4 squared. So now when we graph that first one, y equals parentheses 1 divided by x plus 4 squared. Notice our graph looks like that. It never, at least not there. Oh, there it is. It never goes below the x-axis, but as you get closer and closer to infinity, do you see that you never cross 16 in each direction? That's that base function. So let's draw what that looks like here in our notes. So here's our graph. We have an asymptote out here at 16. We have an asymptote at negative 16. And between those two, we go down to 0, then back up to infinity, and then back down. So we've got a vertical asymptote at 0. We go down to our graph, back up to infinity, and then from negative infinity, coming over. Oops, not negative infinity. It started at positive infinity, didn't it? Yeah, it came down from positive infinity and came over to our asymptote. Then if we graph the other one, y equals 1 over x plus 4 squared, and to turn off the other two, you can see that that graph also never crosses the x-axis, and it has an asymptote at negative 4.
Really?
So an asymptote at negative 4 never crosses the x-axis.
We don't have a review yet, so.
So you can fill in the rest of that table.
Is that review?
And we got done with 20 point A. So on Monday we will start with 20 point B. Almost caught up this week. That's not bad.
We don't have a test on Monday?
Oh wait, today's Thursday.
We don't have a test on Monday? Did I not give us a review?
No.
We'll have the test on Tuesday.
Your office is downstairs, right?
Yep. Ken, I'll be there in just a second.